So good afternoon or good morning, everyone. Thank you for joining us. So today we have the pleasure to welcome Professor Wouter Schellart from the University of Amsterdam. And he's going to tell us almost everything about subduction zone and how the width of a subduction zone modify the dynamics of a subduction zone, and what is the kind of deformation we should expect in the overriding plate. So Wouter, the floor is yours.
All right, thanks very much, Catherine. Yes, so I guess my main interest for many years now has been convergent plate boundaries, collision zones, and also subduction zones. And so this presentation is all about subduction zones. Now, I won't be able to tell you everything about subduction zones because then probably take a few years, but at least in these 45 minutes or so, I'll try to give you some idea of what I've been involved in. And I guess my main interest, which is subduction zones and how they affect the overriding plate. So I'm assuming that most of you will know what a subduction zone is, but here, very schematically, very quickly, subduction zones, one of the two types of convergent plate boundaries. We have an overriding plate, which can be oceanic or continental, downgoing plate, which is oceanic. Downgoing plate sinks into the mantle at the trench. The trench is the plate boundary between the overriding and subducting plate. And as it subducts, it generally also forms a magmatic arc in the overriding plate. And now the part of the subducting plate is actually already in the mantle here. That's generally referred to as the slab, the subducted slab. Okay, what is interesting about subduction zones? Well, many things. One of these things is that we can accommodate subduction in two ways. One way is simply by having the subducting plate move trenchward. So we see here in the left-hand diagram indicated as VSP, where the subducting plate moves towards the trench, and this is one way to accommodate subduction. Now, the other way is by having the plate boundary, the trench and the subduction zone hinge that we see here, the bending zone, move backwards. This is generally referred to as trench retreat and subduction hinge retreat, and that's basically a result of the fact that a subducting plate generally doesn't sink in a down dip fashion, so parallel to its dip angle, but actually also has a component perpendicular to the slab itself. And this backward migration, referred to as slab rollback, is also a way to accommodate subduction. So we have two ways of accommodating subduction: trenchward subducting plate motion and trench retreat. Now, in some unusual cases, we also have subduction settings where the trench is actually not retreating. So you see in this right-hand diagram, but the trench is actually advancing. It's moving towards the overriding plate. So in this scenario, the trench advance is actually taking away from the subduction rate. It's actually reducing the subduction rate. So we will only have subduction in this setting in case the subducting plate velocity, VSP, is larger than VT, the trench advance rate. Okay, so two ways to accommodate subduction. This also has an effect on the flow in the mantle. So as the slab sinks into the mantle, it induces mantle flow. And now this trenchward subducting plate motion, VSP, generally is accommodated at depth by down dip slab sinking, so sinking parallel to the dip angle of the slab. And this induces so-called colloidal flow, where flow occurs around a horizontal rotation axis. So we see here in light blue two colloidal flow cells, one in the mantle wedge, where flow is occurring around a horizontal rotation axis, and another one which is counterclockwise in this setting here, clockwise in the mantle wedge, counterclockwise in the subslab, and this is also related to the VSP type of subduction. Now, the other way to accommodate subduction by trench retreat and slab rollback, this induces another type of flow, which is generally referred to as toroidal flow. So as the slab here has a velocity component perpendicular to its own plane, so either backward or forward. In this setting here, in this diagram, it's backwards. Basically, what happens is mantle material behind the slab is moving out of the way and into the mantle wedge, and this occurs in this toroidal type fashion where this flow, this rotational flow occurs around a vertical rotation axis. Okay, so two types of flow related to the two types of subduction, or the two ways we can accommodate subduction. Now, another interesting question, where do we find subduction zones? Most will probably already know. We find them mostly around the edges of the Pacific Ocean, and we can easily track them simply by spotting the deep sea trenches. So here indicated by these black lines with black triangles, all the different subduction zones, active subduction zones on Earth. And at present, we have about 28 active subduction zones on Earth, smaller ones, intermediate, and also bigger ones. Now look at this plate tectonic map with velocities in the Indo-Atlantic hotspot reference frame. Well, we see a number of subducting plates, large subducting plates, oceanic plates like the Pacific and the Nazca and the Cocos plate. A number of overrunning plates like South America, North America, and Eurasia, for example. And well, what we also spot here is the overrunning plate can be either mostly continental, like the South American subduction zone, or we can have an overrunning plate that is oceanic, like the Philippine Sea plate. And in that setting, then we have ocean subduction. Now, another thing you can see here is all these little numbers here in black, and these black vectors here, and also in gray here. And they indicate the plate velocities in black with numbers in centimeters per year. And in gray, we see here the plate boundary velocity, the velocities of the velocities at the subduction zone trench. So in light gray, we have the trench migration velocity. If it's positive, it means the trench is retreating. And in darker gray, we also see the trench normal component of the subducting plate velocity. Now we can see in this map quite clearly that all these different tectonic plates have different velocities, but also at the actual plate bound, the subduction zone plate boundaries, these velocities vary also significantly, not only between different subduction zones like South America and Scotia here, but also along individual subduction zones, such as we can see here for the Tonga-Kermadec subduction zone. And so one of the things that, well, quite a number of geodynamicists and tectonicists are interested in, including myself, is why do we have this variability in plate velocity and trench velocity at these subduction zones? Okay, what else is interesting and important about subduction zones? Well, one thing, as we already know, for some 45, 50 years almost, is that the fact that subduction zones, and in particular the subducted slabs that sink at these subduction zones, are the main drivers of plate motion, tectonic plate motion, and also mantle flow. So in this diagram that we see here, classical paper from Forsyth and Ueda from 1975, what we simply see here is the average velocity of the major tectonic plates. So here, for example, we see the Cocos plate and the Pacific and the Nazca plate, Indo-Australian and Philippine plate. So the horizontal axis indicates the average velocity, average absolute velocity of these tectonic plates. And on the vertical axis, what we see is the percentage of the circumference of these tectonic plates that is attached to a subducting slab. So how much of a plate is attached to a sinking slab? And now we can clearly see here the plates with very high average absolute velocity have a significant percentage of their circumference attached to a slab, between, say, 20 and 30% or so. And what we can also see is the plates that have a very low velocity, between, say, 1 and 2.5 centimeters a year or so, like Eurasia, North America, South America, Africa, Antarctica, and the Caribbean. They generally do not have any slab attached to them. So this has convinced many geodynamicists and geoscientists in general that subducted slabs are indeed the major driver of tectonic plates, simply due to slab pull forces. So this is one line of evidence. Another one is simply by looking at what the actual velocities are at the subduction zone trench. So here we see a frequency plot. This frequency plot has been made by basically looking at all the active subduction zones on Earth. So there's about 52,000 kilometers of subduction zone, active subduction zone on Earth. And what has been plotted here is basically the velocity along this 52,000 kilometers of subduction zone by looking at individual 200 kilometer segments, trench segments, and basically calculating the velocity and plotting it in this simple frequency plot. So here in the horizontal axis, what we see is the subducting plate velocity, where trenchward is positive and oceanward is negative. And we see from these data points, about 258 data points, we see that about 89% of these trench segments, the subducting plate is moving trenchward. So about 46,000 kilometers or so, the subducting plate is moving trenchward. And so that clearly indicates, again, that slab pull is a major driver of tectonic plates, right? Almost all subduction zones, the subducting plate is indeed moving trenchward, simply because the slab is pulling the trailing plate at the surface towards the trench and into the mantle. Okay, so subduction zones as major drivers of plate motion and also mantle flow. Another thing to note here in this frequency plot on the left-hand side is, again, this variability in VSP, right? The variability in plate velocity. So the highest plate velocities are 9 centimeters a year or so, and the lowest are negative. Okay, so that's for the subducting plate velocity. We also have the trench velocity. Here's a frequency plot of the trench velocity for these, what was it, about 52,000 kilometers of subduction zone on Earth, active subduction zone. And here we see for the trench velocity, we also see quite a significant variability, right? The trench advance, negative is trench advance, and positive is trench retreat. So we see a variability from, say, between -5 centimeters a year up to almost 15 centimeters a year. And what else can we see? We can also see that the mean and the median trench velocity are both positive, and about 70% of all the trench velocities, they are larger than 0, which indicates that on Earth, at present at least, the majority of subduction zones are retreating. So the trench is migrating oceanwards and the subduction hinge and the slab are moving backward. Okay, so interesting and important observations. What else is there to know about subduction zones? Well, that's what we start with and what Catherine already mentioned during the introduction. Subduction zones have variability in the way they deform the overriding plate. And so we have two extremes. At one end of the spectrum, we have subduction zones that form big mountain ranges like the Andes, form orogens, and that's basically this schematic diagram illustrating this. End of the spectrum, so we have an overriding plate, a continental overriding plate. We see a magmatic arc, we see significant crustal thickening, and here in the back arc, we see overriding plate shortening by thrusting and folding. So this would be the, well, one example would be the type example of overriding plate shortening in orogenesis is the South American subduction zone with the Andes. And so on the other side of the spectrum, we see overriding plates that are not shortening, but are actually extending. And what do we have? What happens when the overriding plate extends? Basically, we form a back arc basin. So here we have the subducting plate, the overriding plate, the magmatic arc, and what we see quite often in nature is behind this magmatic arc, we have a back arc basin, which forms by crustal thinning, so horizontal extension, perpendicular to the trench axis, and we also see normal faulting. So two end members, overriding plate shortening and overriding plate extension. So the first one forming an orogen, like the Andes, and the other one forming a back arc basin. Okay, now if we look on a global scale, in this global tectonic map, if we just color code those subduction zones that are experiencing shortening in red, and those that experience extension in blue, and the ones that do not experience that much overriding plate deformation in green, then, well, we see this pattern here. And, well, in general, I've shown this map. I show this map also when I'm teaching my bachelor and master students. And then generally I ask them a question, well, what do you see? What do you observe here? What is peculiar here in this map? So maybe to get a bit of interaction here, I can ask you as well, the audience here, what is peculiar about this map? Many things, but I guess I'm trying to get to one particular answer. So something that you notice in this map, but just look at the colors, the distribution of the colors. Who is brave enough to try and answer my question? Anyone? No one? Okay, I'll give you 10 more seconds. What do we see? We look at just to look at the colors, the blue, the green, and the red. And in particular, the blue and the red, because they're the most interesting. Okay, well, the main thing, I guess most students in my class, they're also maybe a bit too shy to answer, but the main thing that you'll see here is that there's actually much more blue than there is red. There's only a few locations on this map where we see red, where the overriding plate is shortening, and many more locations, many more subduction zones where we actually see blue. So overriding plate extension is more common than overriding plate shortening. And that's also what we see in this next slide here, where we see this frequency plot. So again, vertical axis frequency, horizontal axis shows the overriding plate deformation rate, where positive is extension and negative is shortening. So again, we have 258 trench segments, each about 200 kilometers in extent. So again, about 52,000 kilometers of subduction zone, and for these 52,000 kilometers of subduction zone, about 34% the overriding plate deformation rate is positive, and so we have an extending overriding plate. We form a back arc basin, and only about 16% show that the overriding plate deformation rate is smaller than 0. So we actually experience shortening. And then about half, about 50%, the overriding plate is not doing very much. So those were the green colors in the previous slide on the map, in the previous slide. Okay, so that's an interesting observation and something, yeah, you might want to answer, in particular, if you're a geodynamicist. And so a lot of geodynamicists and tectonicists and geologists and earth scientists in general have been thinking about these types of questions and have developed different types of conceptual models and geodynamic models, in particular to try and answer questions as to what might actually affect these different velocities, right? These subducting plate velocity, the trench velocity, and the overriding plate deformation rate, and what actually might explain their variability. Variability along different subduction zones and also between different subduction zones. And so here we see a whole list of parameters that have been investigated, and the list is much longer than the parameters that I show here. And also, obviously, due to time constraints, we won't be able to go through all these parameters. So now I'll just focus on two parameters, basically slab age, the age of the subducting plate that is sinking at the trench, and the subduction zone size, in particular, expressed as the trench parallel slab width, so the width of the slab measured along the trench. Okay, so slab age has been thought for a long time to affect the plate velocity, subducting plate velocity, trench velocity, and overriding plate deformation rate. And in general, it's not very complicated, the conceptual model. The general idea is that for old slabs, old oceanic lithosphere subducting at the trench. So think of the Western Pacific here, where we subduct Cretaceous and Jurassic oceanic lithosphere. Old slab is generally thought to be very thick oceanic lithosphere, thought to be relatively dense, so much denser than the underlying sublithospheric mantle. And the general idea is that, well, because it is high density contrast, we have rapid sinking, and so we have significant slab pull, so we'll have rapid trenchward subducting plate motion, we'll have rapid trench retreat and slab rollback, and this will then induce overriding plate extension. And so this was first proposed by Molnar and Atwater in a famous paper in 1978 already, so about 45 years ago. So that's for old slabs. Then for young slabs, which are located more in the Eastern Pacific, young slabs are generally relatively thin, are relatively light, so the density contrast with the underlying mantle is much smaller, so they might only have a small density contrast, or might be closer to neutrally buoyant. So the slab pool is thought to be smaller, which results in slower trenchward subducting plate motion, generally no trench retreat, no slab rollback, and so higher coupling at the subduction zone interface at subduction zones, and therefore we might expect overriding plate shortening. Okay, so this model has been very popular for a long time, and it's still quite popular amongst many geoscientists. But if we look at data, the actual data, then it seems that this conceptual model actually is not all that convincing. So what we see here is just 3 plots. Again, plots for all these active subduction zones, 28 in total, and basically representing some 52,000 kilometers of active subduction zone. And what has been plotted on the horizontal axis for these 3 diagrams is the age of the oceanic plate at the trench. So from 0 on the left-hand side to 180 MA on the right-hand side. And then for the top left diagram, the vertical axis VSP. The right diagram, we see VT on the vertical axis. And then the bottom diagram, we see the overriding plate deformation rate along the vertical axis. Now, we see for VSP, if we go to the top left diagram, we do see a positive correlation between increasing subducting plate age at the trench and VSP. This dashed line is just a simple least square linear best fit line. But we can also see that the correlation is actually not all that high. It's not super convincing, at least to me it is not. For the overriding plate deformation rate, there's also a positive correlation, but the correlation coefficient is even much smaller. So in general, low correlation coefficients. For the trench velocity, the correlation is somewhat better, but as you might already notice here, the correlation is actually opposite to what the conceptual model predicts. The conceptual model would predict that with increasing age, the trench retreat velocity would increase, so positive slope, positive correlation. What we actually see here is a negative correlation. It's not a very large correlation, not very high correlation, but it's actually opposite to what you'd expect if this conceptual model, if you'd accept this conceptual model. Okay, so low to very low correlations and an opposite correlation here for VT, opposite to what this conceptual model would predict. Okay, so that's so far slab age. What about slab width? How might this affect VSP, VT, sorry, and VOPD? Well, the general conceptual model, again, is not very complicated. Excuse me. The idea is we have a relatively narrow slab, as shown in this schematic diagram here. If we have a narrow slab, then the lateral slab edges. Here we have a lateral slab edge on one side, and here we have the lateral slab on the other side, the lateral slab edge. If we have a narrow slab, then in general, we have efficient toroidal return flow. So a slab, as it retreats during slab rollback and trench retreat, it's quite easy for subslab mantle material to flow from the subslab region into the mantle wedge region due to this toroidal return flow. So there's relatively low resistance to slab rollback. If there's low resistance to slab rollback, this will promote a high trench velocity and a relatively low trench subducting plate velocity. So most subduction is accommodated by trench retreat, not by trench subducting plate motion. And this high trench velocity itself would then promote extension in the overriding plate, so back arc extension. Now, if we have a very wide slab, so this subduction zone would be much wider, then expect toroidal return flow to be quite inefficient, simply because the pathway from the subslab into the mantle wedge would be much larger because the slab is very wide. So we have inefficient toroidal return flow, high resistance then to slab rollback. So this would promote subduction through VSP, right, through trench with subducting plate motion. It would promote a low trench velocity, and thereby it would induce shortening in the overriding plate. Well, that's the general idea. Okay, so if we look at these similar diagrams as we shown earlier for slab H, but now for slab width. So the horizontal axis here, what has been plotted is the width of the slab from very narrow here, like a Scotia subduction zone, to very wide here, which is more like a South America or a Sunda subduction zone. We see there's actually a positive correlation for VSP, right? The wider the slab becomes, the larger the VSP, the larger the trench with subducting plate motion. For the trench velocity, we see, as predicted by the conceptual model, a decrease, a negative correlation. So very wide slabs generally retreat slowly, whilst wider, narrow slabs retreat faster. And then for the overriding plate deformation rate, we see that wider slabs tend to correlate more with overriding plate shortening, whereas narrow slabs tend to correlate more with overriding plate extension. Now, admittedly, here the correlation for VOPD is not very significant, but it is more significant than for slab H, and certainly for VSP and VT, the correlations are significantly better than for the slab H parameter. Okay, so better correlations than for slab H. So in general, a parameter that is, in my view at least, worthwhile investigating. So let's have a look at two extremes, two examples of subduction zones, one with a very wide slab and one with a very narrow slab. The wide slab type example is the South American subduction zone, where we find this massive Andean origin, right, about 7,500 kilometers from north to south, from Colombia in the north to Patagonia here in the south. Now, what's remarkable about the South American subduction zone? Well, first, as I already mentioned, it's very wide, 7,500 kilometers from north to south, so measured along the trench here. And it's also very long lasting. It's been active for at least 200 million years. Geologists argue it's been active at least since the early Jurassic and possibly already since the Triassic. So long-lasting continuous subduction here along the trench. So those are two peculiarities. Another one is that we also have very deep subduction in South America. So here we have a profile, east, west to east profile. Here we have the subducting Nazca plate. And as we see in this seismic tomography cross-section, a P-wave seismic tomography cross-section, we see that the slab here indicated or interpreted by most people as these blue regions here, we see that the slab actually sinks very deep into the lower mantle, possibly down to, well, more or less the core mantle boundary. Okay, so it's very wide, it's very long-lasting, and it's also very deep. If we now go to another subduction zone that is characterized by massive back arc extension. That's basically the best example here is the Scotia subduction zone in the southern Atlantic. So here we see the Scotia subduction zone, the magmatic arc here, and here behind it we see a massive back arc basin. Now, what is remarkable about the Scotia subduction zone, or peculiar, its main traits, basically, we have a very narrow subduction zone, 700-800 kilometers measured along the trench, so an order of magnitude smaller than the South American subduction zone. And if we look at a cross-section along here, seismography cross-section, we see that the slab is actually quite shallow. It's flattening more or less at or just below the 660 discontinuity. Okay, so relatively narrow and also relatively shallow. And what is actually not mentioned here, it's also not very old. Depends a bit on who you ask, but in most tectonic reconstructions, the age of the Scotia subduction zone is somewhere between 30 and 80 million years of age. So certainly much younger than the South American subduction zone. Okay, so summarizing here, South American subduction zone, high VSP, low VT, bordered by a massive mountain range, resulting in major shortening. Large subduction zone, 7,500 kilometers, long-lasting since the earliest Jurassic or late Triassic, and deep subduction down to 2,400, 2,800 kilometers. And the Scotia subduction zone, what do we find? Low VSP, high VT, so subduction mostly accommodated by trench retreat. Bordered by Scotia Sea Becker Basin, resulting from massive east-west extension. A narrow subduction zone, about 800 kilometers, measured along the trench, and also relatively shallow subduction. So we can also see that nicely summarized in this diagram here. Large South American subduction zone, small Scotia subduction zone. Here we see in red the trench velocity and in blue the subduction plate velocity. So subduction here is mostly accommodated by trench retreat, not by trench with subduction plate motion. And for the South American subduction zone, that's the opposite. Most subduction is accommodated by the Nazca plate moving westward, and only a small percentage is accommodated by the actual trench moving, the Nazca plate moving eastward, I should say, and the trench retreat accommodates only a small amount of subduction with slow trench velocities towards the west. And here in the center, actually slight trench advance towards the east. Okay, so the two extremes. Okay, so what can we do to try and get some more quantitative understanding? Well, we can try and run some interesting geodynamic models. So we can either do that in the lab using analog models, or we can do it on a computer using numerical models. And here I'll just show some results from some numerical models conducted with the Underworld code developed in Australia by Moresi and colleagues. So what's the general idea? We have a very large modeling domain, a three-dimensional modeling domain. We have an overriding plate, somewhat mimicking a South American type overriding plate, so a continental overriding plate with a continental crust and a lithospheric mantle, overlying low viscosity nonlinear upper mantle, and this overlying lower mantle with a Newtonian viscosity, all the way down to the core mantle boundary at around about 2,900 kilometers depth. And then we also have a subducting plate here in darker gray, here indicated in blue and these gray, different layers with different viscosities, and a top layer that is viscoplastic. And the subducting plate is simply negatively buoyant with respect to the underlying sublithospheric mantle. And so the experiments or these numerical simulations are basically entirely buoyancy driven. So there's no imposed velocities. It's all just driven by density contrast within the modeling domain. Okay, so this is the setup. The main things is three-dimensional, it's buoyancy driven, and we have a very large mantle domain from the surface down to 2,900 kilometers. And what's the thing that we vary? We simply vary the trench parallel extent of the subduction zone. So the slab width is varied from 600, so that's a bit like a Scotia subduction zone, up to 6,000 kilometers in width, which is a bit more like the South American subduction zone. Okay, let's have a look at some results. So here we see a cross-section, and here we see a 3D perspective view. The cross-section, both are for the narrow subduction zone model, 600 kilometers, so the Scotia-like subduction zone. This shows the viscosity field in the cross-section. It's a cross-section through the center of the subduction zone. And this one here shows the strain rate in the subducting and overriding plate. Okay, so what do we see? We see that the subducting plate here is sinking into the mantle, as one would expect, because it has a high density, it's negatively buoyant, so it wants to sink into the mantle. And we see that as it sinks into the mantle, we see that in this narrow slab subduction setting, the subduction is almost entirely, or mostly accommodated, I should say, by trench retreat and subduction hinge retreat and slab rollback. So the trench is retreating very rapidly towards the west, and it's only slow eastward motion of the subducting plate. So VT is much larger than VSP. We can also see that as the trench retreats, the overriding plate here is extending here in this back arc domain. This region here is, well, becoming longer, we can see. So we have massive overriding plate extension and back arc basin formation. You can also see it here in the strain rate field here with relatively high strains here in the back arc region. What is also interesting to note is as it retreats, the slab retreats and rolls back, we see basically being draped on top of the 660 discontinuity here. And we see that it's not a continuous flat lying slab, but actually it shows this periodic folding, nice periodic folds as it is draping backwards over the 660 discontinuity. Okay, so this is the narrow slab subduction model. Let's have a look at the wide slab subduction model. So a bit more like the South America style subduction model. What do we see? We see, well, again, we see the subducting plate here sinking into the mantle as it's negatively buoyant. We see that subduction here is accommodated quite differently from what we saw in the previous slide. Subduction now is accommodated to a much larger extent by trench-rich subducting plate motion. So the VSP here is much larger than the VT. Most subduction is accommodated by the plate moving towards the trench, the subducting plate moving towards the trench, and the trench is retreating, but it's retreating at a slower rate than for the narrow subduction model. What else do we see? Well, we see that the overriding plate here is deforming. We see that initially, actually, during the initial upper mantle subduction phase, the overriding plate is extending, and only once the slab enters the lower mantle, do we see the overriding plate shortening. Here we see again, very briefly, initial phase of back arc extension during upper mantle subduction. And now as the slab is sinking into the lower mantle, we see that the overriding plate is shortening. We see this zone here, this back arc zone, actually becoming shorter and shorter. Right, so here we have an initial phase of extension, and once the slab starts to sink into the lower mantle, past the 660 discontinuity, the overriding plate here is shortening, becoming shorter. Okay, interesting. So narrow slabs have a high VT, slow VSP, and are characterized by back arc extension. The wide slab model is here in the bottom, characterized by high VSP, low VT, and in general, overriding plate shortening except for the upper mantle subduction phase. So how can we explain this? Well, we can explain it by simply looking at the velocity fields in the mantle. And that's shown in these two cross sections here. The top one is for the narrow subduction model, so Scotia-like, and the bottom one is for the wide subduction model, so the South America type subduction model. So this is for the upper mantle phase, right? Quite early in the subduction model evolution, 18, 19 million years into the model evolution. And what do we see? The colors here indicate the velocity magnitude. So red is high velocity magnitude, and yellow, green, and blue is lower velocity magnitude. We also see the velocity vectors here. And what do we see during this upper mantle subduction phase? We see most of velocities, the high velocities are concentrated in the upper mantle, as one would expect. And if we look at the velocity patterns here below the overriding plate, then we can see that they're actually reasonably comparable for both subduction models. So we see very large velocity vectors directed towards a trench here in the near back arc, so close to the trench, and very low small velocity vectors are also directed towards the trench, but the velocity vectors are much smaller in magnitude here in the far back arc. And we see the same here for the wide subduction model. Trenchward directed velocity vectors, very large here in the near back arc, so close to the trench. The trench is here, this is the slab. And here in the far back arc, we see much smaller trenchward directed velocity vectors. So what does this do? It simply creates a basal shear gradient at the base of the overrunning plate, where the leading part of the overrunning plate is being dragged trenchward very rapidly in this case, in both models, so the narrow and the wide subduction models. We have significant basal drag, basal shear tractions here close to the trench, and much smaller basal shear tractions far from the trench. And this gradient in shear traction simply pulls the overrunning plate apart, right? We get tensional stresses in the overrunning plate, and basically we extend the overrunning plate and generate a back arc basin. So that's for the early subduction phase, the upper mantle subduction phase. If we now go to the later phase where the slab is actually sinking into the lower mantle, so the 660 discontinuity is approximately around about here. So in both scenarios, the slab has penetrated the lower mantle. So again, this is the narrow slab model at the top, and the bottom shows the wide slab subduction model. And now we see very different velocity patterns for the wide slab model. So the narrow slab subduction model, we see basically the same basal shear traction gradients here below the overrunning plate, with significant trench-directed shear tractions here in the near back arc, and very minor trench-directed shear tractions here in the far back arc. So this positive towards the trench, positive shear traction gradient again continues to extend the overrunning plate. But if we look at the wide slab subduction model, we actually see now the opposite. So the slab is actually sinking well into the lower mantle. What does it do? It generates a very large scale colloidal return flow here, mantle scale colloidal return flow, counterclockwise. And we see here as the slab sinks, the velocity vectors here are directed towards the, inclined towards the overrunning plate side. That's why we have this very strong colloidal return flow here below the overrunning plate, and a much weaker colloidal return flow here below the subducting plate. So this is a very strong colloidal return flow. And what does it do? It basically creates a pressure gradient here in the upper mantle. And the pressure gradient causes the flow here in the upper mantle to actually, the velocity vectors to decrease towards the trench. So in the far back arc here below the overrunning plate, we have very fast trench-directed velocity vectors. And here in the near back arc, so close to the trench, the velocity vectors are much smaller. So now we actually have a negative basal shear traction gradient below the overrunning plate, so opposite to what we have for the narrow slab subduction model. So here we have a positive shear traction gradient, and here we have a negative shear traction gradient. And this negative shear traction gradient basically causes the overrunning plate to shorten. This part is being dragged trenchward very rapidly. The near back arc is being dragged trenchward much more slowly, and so the overrunning plate experiences compression. And at the same time, another thing that adds to the overrunning plate compression and shortening is the fact that the overrunning plate is actually being dragged trenchward at a faster rate than that the subduction zone hinge itself wants to migrate oceanward. And so here we also have very high compressive stresses at the subduction zone interface. Okay, and then this is an even later stage where we still see the same shear traction gradients. So positive here for the narrow slab model and negative for the wide slab model, inducing tension and extension in the narrow slab model, and compression and shortening in the wide slab model. Okay, so we can also plot this in a simple diagram to maybe make it even more clear. So what has been plotted here on the left-hand side is the velocities and the shear gradients and the shear rate and the shear gradient below the base of the overriding plate for a zone, basically 150 kilometer thick upper mantle zone between the base of the overriding plate and this red line that we see here. So this is for the narrow slab model on the left-hand side. On the right-hand side, it's for the wide slab model. And so this here shows the velocities in the overriding plate in orange and the velocity in the mantle at 150 kilometers below the base of the overriding plate in red. The same here, but then for the wide slab model, the velocity in light blue of the overriding plate, and in dark blue, the velocity of the mantle, the horizontal velocity in the x direction here at 150 kilometers below the base of the overriding plate. And so from this, we can get the shear rate below the overriding plate. And from the shear rate, we go to the bottom two diagrams. So we can get the gradient in horizontal shear rate at the base of the overriding plate. And we can see here the difference in shear rate gradient. It's basically the horizontal gradient towards the trench of the shear rate below the base of the overriding plate. We can see for the narrow slab model close to the trench here, the shear rate gradient is actually positive, and this positive gradient induces extension in the overriding plate. Whilst for the wide slab model, it's mostly negative here, indicated here in these sort of blue bands here, these blue regions. And so this induces shortening in the overriding plate. Okay, so it's basically mostly the result of differences in mantle flow that causes the difference in overriding plate deformation style. Okay, this plot then simply shows the evolution of overriding plate deformation rate. Again, here we have the time, the horizontal axis from start of the model 0 towards the end of the model 120 million years. And the vertical axis is basically the average overriding plate deformation rate. And then for three models, the orange one is for the narrow subduction zone, so the Scotia-like subduction zone. In blue, it's the wide subduction zone, the South America style subduction zone, and then in black also plotted is an intermediate width subduction zone. So it would be a bit more like the Central America subduction zone, for example, in terms of size. So we see for the narrow Scotia-like subduction zone, we see only positive values, and positive values indicate extension, right? And we see again very clearly this periodic signal here, which relates to the falling of the slab at the 660 discontinuity. And in blue, we see for the wide subduction zone model, we see an initial phase of extension, which is during the upper mantle subduction phase. And then at some point around 40 million years into the model run, when the slab has sunk quite deeply into the lower mantle, and we generate this large colloidal return flow, we see that the overriding plate is dominated by overriding plate shortening, horizontal shortening and compression. Okay. These diagrams, what do they show? They also show on the horizontal axis the time of the model run, and the vertical axis shows the finite deformation, so the cumulative deformation in the overriding plate. And so for the narrow subduction model in orange here, we see at the end of the model run, we've extended the overriding plate by some 1600 kilometers or so. And for the wide subduction model in blue here, we see an initial phase of extension, some 250 kilometers of extension up until 40 million years. And then following that, we see that the overriding plate is shortening down until the end of the model run, where the finite shortening is of the order 350 kilometers or so. Okay, so these data points or these lines here are for the center of the subduction zone model. What is interesting for the very wide subduction zone model is that the deformation actually varies along the subduction zone. So in the center of the subduction zone, that's this dark blue line here, the same one is plotted here, the amount of shortening is actually more significant than the amount of shortening that we have if we look at the lateral slab edges. So this dashed blue line here indicates the amount of shortening or the amount of deformation, the finite deformation in the overriding plate close to a lateral slab edge. So we see, first of all, that the change from shortening to extension occurs at a later stage if we are located close to a slab edge rather than in the center of the subduction zone. So here the change occurs at 40 MA, 40 million years. And here the change occurs, well, you can say either this is the change or maybe this is actually the change from shortening to extension. So the change from shortening to extension occurs much later. And also we can see that there's a bit more sort of periodic variability in terms of deformation if we look at locations close to the lateral slab edges. So the negative slope is basically indicates shortening in the overriding plate, but here we see this positive slope indicates the short period again of extension. And here we have a negative slope indicating shortening, and here we might have this very short phase of extension again in the overriding plate. So for wide subduction zones, it's all a bit more complicated. It's not as straightforward as for a narrow subduction zone. You actually have variability along the trench in terms of the deformation rate, and also in some cases the deformation style. Okay, that's quite interesting. What does this plot show? This plot shows the horizontal deviatoric normal stress in the overriding plate. Again, for the narrow slab model in orange, the wide slab model in blue, and also plotted in black, the intermediate width subduction zone. The top diagram here shows an early stage of the model runs, so the upper mantle subduction phase. The middle one shows an intermediate stage when the slab is sort of just starting to penetrate into the lower mantle. And the bottom panel here shows an advanced stage of the subduction model where the slab is well into the lower mantle. So we can see for all three models in the upper mantle subduction phase that the overriding plate experiences deviatoric tension. I forgot to mention the horizontal axis here indicates the distance from the trench. So this is the trench location, T, and this is 1,000 kilometers from the trench, etc. And the vertical axis shows the deviatoric horizontal normal stress with positive values indicating tension and negative values indicating compression. All right, so positive numbers, tension only in the overriding plate during the upper mantle phase, subduction phase for all models. As the slab starts to sink into the lower mantle, we see for the orange line, the narrow slab model, stresses are still tensional, but for the wide slab model, they're close to neutral, close to zero. And then here, the bottom diagram, the late stage of the model run, when for all models, the slab is well into the lower mantle. We can see still tensional stresses for the narrow slab model, but the wide slab model shows significant overriding plate compression. The stresses here, up to about, 70 megapascals of compression compared to during the tensional phase. What we can see here is approximately 80 megapascals of tensional stresses here in the early subduction phase. Okay, so these are sort of order of magnitude stresses that we find in these numerical models. And then here, what I forgot to mention as well, sorry, these stresses were all measured at the top surface of the overriding plate. But here we can see the actual stresses distribution within the overriding plate. And we can see here the color scheme here indicates orange and red, clear tensional stresses. So this is the final stage of the subduction models. This is the narrow slab model. We can see red and orange colors here. So entirely tensional, deviatoric tension in the overriding plate. And this is for the wide slab model towards the end of the model run. We can see green and blue colors here. So more or less entirely compressional in the overriding plate for this wide slab model. Okay. Interesting. So coming to some sort of schematic representation of the actual mechanism at play here. What do we have for narrow subduction zones? So that's the top schematic sketch here. What do we have? So we have a narrow slab. Narrow slabs are happy to retreat rapidly through the mantle, happy to roll back rapidly through the mantle. So the slab retreats rapidly because the ambient mantle here can easily be pushed out of the way and flow from the subslab into the mantle wedge. This toroidal return flow is facilitated. It's quite easy. There's relatively minor resistance for this toroidal return flow for narrow slabs. And so as the slab falls back, the hinge retreats and the trench retreats as well. And this first of all induces deviatoric tensional stresses here at the subduction zone interface. And with it, as we saw, this toroidal flow also induces a strong positive trenchward basal drag gradient. Right, so the basal drag here near the trench is very high, and far from the trench, the basal drag is quite small. And so this positive gradient causes deviatoric tension and extension in the overriding plate. And so for the wide slab model, it's very different. The slab is very wide, so it's quite difficult. There's a significant resistance from the subslab mantle here to move into the mantle wedge to allow for this slab to retreat. So rather than actually sinking through trench retreat, the slab rather sinks through trenchward subducting plate motion. So VSP is very high and VT is relatively limited. And this downward sinking of the slab causes the slab to form this significant folded slab pile. This folded slab pile here sinks asymmetrically in the lower mantle. There's no vertical sinking, but it actually sinks at an inclined angle towards the overriding plate side. So this inclined angle here, this generates a very strong poloidal return flow here below the overriding plate, whilst the return flow below the subducting plate here, this poloidal flow cell is much weaker. So this strong poloidal return of flow cell generates a gradient in the mantle pressure here in the upper mantle, and this causes trenchward flow here in the mantle far from the trench to be much faster than here close to the trench. And so now we get a negative basal drag gradient at the base of the overriding plate, and this induces compression in the overriding plate. And what adds to this compression, as I mentioned earlier, the overriding plate moves trenchward at a faster rate than that the hinge, subduction hinge, actually wants to retreat. So we generate additional compressive stresses here at the subduction zone plate boundary, causing compression and shortening in the overriding plate. Okay, so coming to a conclusion here. Subduction kinematics. What do we have? Wide subduction zones, generally characterized by a high VSP, so high trenchward subducting plate motion, and low VT, low trench retreat velocities. Narrow subduction zones, on the other hand, are characterized by low trenchward subducting plate velocities and high trench retreat velocities. What else do we have? In terms of overriding plate deformation, what are the requirements to build a massive Cordilleran origin like the Andes? Well, it seems that we need a very large subduction zone, 8,000 kilometers in trench parallel extent. We need long-lasting subduction, so significantly longer than 50 million years of subduction. And we also need to subduct deep into the lower mantle. And what are the requirements for back-arc basin formation? Well, in general, we can have a very narrow subduction zone that retreats happily backwards at rapid rates, so less than, say, about 2,000 kilometers. But what else? What are other scenarios where we can actually generate back-arc extension and back-arc basin formation? We saw in one of the diagrams that near lateral slab edges, we can extend the overriding plate for longer, even at wide subduction zones. And we also saw that at wide subduction zones, if we're only in an early stage of subduction, so an upper mantle subduction stage, we will then also generate overriding plate extension and a back-arc basin formation. Okay, so that brings us back to this this slide here that I showed earlier, and I tried to ask you a question. Again, about the color schemes that we see here, right? We see red, we see blue, we see green. See about 50% of green, subduction zones that do not deform very much. They're the least interesting. What are the most interesting subduction zones? They're either red or blue, right? These are the subduction zones where the overriding plate is extending or shortening. And we saw in the frequency plot that there's more or less, well, there's more than twice as many subduction zones that are experiencing extension than subduction zones that experience shortening. And so why is that the case? Why do we have more extension than shortening? Well, I guess that brings me back to the previous slide, and I guess the main conclusion of many of these slides that I've shown you and the numerical modeling exercise that I've done and presented to you is basically related to the fact that to generate overriding plate shortening, you need to have very specific circumstances to allow overriding plate shortening to occur, right? You first of all need a very large subduction zone. There are not that many large subduction zones on Earth. Here we have the South American subduction zone. We have the Northwest Pacific subduction zone, from Kamchatka down to the Marianas. We have the Sunda subduction zone, and we have the Melanesia subduction zone. So we're going to have 4 big subduction zones on Earth at present. But this is not enough. We need more than a big subduction zone. We also need to have very long-lasting subduction, and we also need very deep subduction. And so from these 4 large subduction zones, only the South American subduction zone has been active for very long and also has been subducting very deeply into the mantle. So if you think about the Sunda subduction zone, for example, it's been active only for about 45 million years. So it is very wide, but it actually only has been active for a short time. So we don't have significant subduction into the lower mantle, and therefore we haven't developed this massive colloidal return flow yet. And the same goes for Northwest Pacific and Melanesia. Northwest Pacific is interesting because at present now in Japan, we see actually some overriding plate shortening here in the island of Honshu. And so it might be that this Northwest Pacific subduction zone is now in a stage or a phase where it is actually changing from a subduction zone that is initially characterized by overriding plate extension as these backarc basins formed, including the Japan Sea, and now as the slab, because it's a very wide slab, as it's slowly sinking into the lower mantle, we might actually be starting to change from a region or regime of overriding plate extension to a regime of overriding plate shortening. And that's all I have to say. Thank you very much, everyone, for your attention and attending this seminar on subduction zones.
Well, thank you very much, Wouter. It was really interesting. I'm going to open the question time. So anyone who wants to ask a question, put that in the chat or raise your hand and unmute yourself. No question? Okay. So maybe.
Hello. Hello. I have a question, but first, thanks, Wouter, for the talk. It was very interesting. I'm very glad that I got the link from for this talk through a mailing list. So, well, I have a question, and it's regarding my work of the PhD, doing my PhD in France. And I'm currently working on the northern end of the subduction zone in South America, in Colombia. So, well, in the last slide you showed, it's labeled as a green zone, like a neutral zone. So, well, at these latitudes, the slab encounters 2 other slabs in the Caribbean and the Central American zone. And I'm trying to explain what happens with the South American slab here, as there is some evidence of oceanic plate fission. And we could imagine like younger and narrow subduction zones going behind older and wide subduction zones. So my question is, what could be the effect of a transition between older and wide and narrow and younger in the overriding plate deformation, like both along the trench and along deep? So like, I wonder if this could result in like a fading subduction zone towards the north, while transferring some kind of deformation along crustal faults. And I extend my question in the sense that here in this area, we still have some signatures of deep subduction and some seismicity too in greater depths.
Yep.
So yeah, I wonder how could you explain the effects of a slab that is not wide anymore, and yeah, if you can have some insight on this transition or phenomenon.
Yeah, it sounds like a very complicated little corner. So I'm assuming you're talking about this corner here.
Yeah.
And so you're saying that there is, apart from the Nazca plate subducting here, there's also another narrow slab subducting here?
Yeah, what I mean is that is like the northern end of the Nazca plate.
Yeah.
So it's like a wide and old subduction zone, but at this point where there is like a triple junction between at least three plates, South America, Caribbean, Nazca, there is some how to say, this subduction when we see the Nazca plate in the I mean land, ocean, in the ocean side.
Yep.
There are some fission tracks in the slab, I mean in the plate, before arriving to the trench. So this could kind of imply that the subduction zone in these latitudes is breaking off. Is I mean that for example, how to explain that the behavior of a wide subduction zone in this region changes from wide to a narrow and localized subduction zone right next.
Right. So with fission, you mean fracturing or?
Yeah,
or
fracturing
breaking?
of the.
Okay, right, now I get it. Okay. Yeah, interesting. So maybe this little fragment here you're saying of the Nazca plate is actually breaking off the major part of the Nazca plate and becoming an individual microplate. Is that what you're saying?
Yeah, is that, but I mean that fission is younger, way more younger than the Nazca plate itself. So at some point in time, it was the same plate.
Yeah, sure. Yeah, that's interesting. So if the Nazca plate fragments into smaller plates, then well, I guess the modeling predicts that the smaller plates will start to behave, and actually also if at depth the slab starts to tear and fragment into individual slab segments, then at some point these little slabs will they'll start to behave. These broken segments will start to behave like small narrow slabs, and then they'll, in that sense, promote overrunning plate extension rather than shorting. But I guess it depends to a large extent on how large the gaps will become between the individual slab segments. So if there's significant gaps such that toroidal flow can actually go through these slab tears, then the Nazca slab will not behave as one major single entity, but you'll actually see that it will start to behave as individual slabs with maybe one large Nazca slab here in the south and an individual minor slab here that is broken off. And then you'd expect, at least from what the modeling predicts, that it changes from rather compressional setting and a regime where you have overrunning plate shortening to a regime where you'd expect to have overrunning plate extension as the slab becomes narrow. It'll find that it tends to want to subduct through trench retreat and not trench with subducting plate motion. And so in a way, this is, I guess, similar to what has happened in the past when the Nazca plate still formed part of the, what was it again? The Farallon plate. I'm not sure if you're familiar with that history.
Yeah.
So the Farallon plate was a massive oceanic plate that included the Juan de Fuca plate and the Cocos plate and the Nazca plate. And then some 50 million years ago or so, it started breaking up because the spreading ridge here approached the subducting zone and it broke up into individual oceanic plates. And that might have been the reason why, for example, the North American Cordillera that formed here up until about 50 MA stopped forming, and the regime here changed from shortening in the Laramide and the Sevier orogeny, changed from that to the basin and range type of deformation with basin and range extension in North America, I think since the Middle Eocene or so. So yeah, fragmentation of subducting plates and slabs at depth will, I guess, change the regime from one that is compressional and showing subducting zone orogeny to one that is more inclined to show overrunning plate extension and tension. So I hope that sort of answers your question, or at least is of some help.
Yeah, it gives me a bit more insight on how to unravel this issue that I have. Okay.
But yeah, it is a very complex region, that's for sure, because you have all these different subduction zones that come together here. The Venezuela subduction zone here, and the southern end of the South American subduction zone, where you also have this, what is it called, the Cocos spreading ridge approaching here. So it is a very complex setting, that's for sure.
Okay, well, thank you.
Yep, no worries.
Any other question? Okay, maybe I'll ask a couple.
Yeah.
Yeah, so I was wondering if you could extract some scaling for a critical width with all the parameters of the model to say, okay, at that critical width, we'll change from one mode to another.
Yeah, possibly. I haven't done that, but it is possible. What I've tried to do in the past was to find some simple scaling relationship for the variability in VSP and VT, which we didn't actually discuss. And that's what you see in these diagrams here, where you have the best fit line here is simply least squares linear best fit line, the dark gray, but the light gray here is actually a sort of a scaling formulation, trying to find the best fit for the scaling formulation with all the data points. And it works reasonably well, although the correlation is actually a bit less. But it works better if we, rather than thinking of all these individual subduction segments, we actually average these velocities for individual subduction zones. And yeah, this scaling formulation is simply a sort of a derivation of the Stokes sinking velocity. So that works quite well. But for overrunning plate deformation, it will be harder to try and formulate these, I guess.
Maybe it's because in the Stokes sinking velocity, we should somehow introduce a length ratio, width by depth of the upper mantle, or I don't know. I have to think, but it would be great to have that kind of scaling for the transition.
Yeah. But well, I guess one of the difficulties, I guess, with with nature is, and also these models, which makes the scaling harder, is that the slabs, the bigger they become, the less they the slabs themselves deform as well, so they're not like rigid entities. Not like your Stokes sinking ball, which is a rigid entity, right? That the slabs deform as they sink.
But the lower mantle is still Newtonian, right?
Yeah, sure. And another complication, I guess, is well, that's what I sort of try to show with this diagram here, is that along individual subduction zones, the bigger they get, the more variability you get along individual subduction zones. So as one part of your big subduction zone, the central part might, for example, at this point in time in your model, right, at 80 MA, it might actually could be experiencing shortening. Or no, let's take this point here, 70 MA. So we have a negative slope here. So your overriding plate here is shortening in the center of your subduction zone. But here we see a positive slope, and this is a line for the lateral, close to the lateral slab edge. Here we have a positive slope, so at this point in time, actually the overriding plate is extending. So yeah, at the same point in time, different locations of the same subduction zone are doing different things in terms of their deformation.
Yeah.
So the bigger the subduction zone becomes, the more significant this becomes.
Yeah, true. Actually, it's great you're showing this, because I had a question with this graph. I was wondering if actually along the Nazca plate, you could find a difference of deformation in the overriding plate versus, let's say, the central part and the edges itself. I mean, what the observation tell us about this deformation regime along the Nazca plate, like central versus edges, or is it by the tiers we have, or something?
So you're asking about the deformation rates in the overriding plate?
Yes.
Yes.
Do we see a difference between, let's say, the central region of the slab and the edges of the slab, if we consider there is no tiers in this?
So well, geologists and also from present day geodetic investigations, what is clear is that here in the central Andes, you have the fastest shortening rates. And if you go away from this central point, so this is the Bolivian Auric line, if you go southward, the shortening rates decrease. And also if you go northward, the shortening rates decrease. And in addition, so this is based on geodetic observations, so more or less present day, but also the geological investigations, just structural geological investigations by looking at balanced cross sections, so crustal balanced cross sections. What they found out is that in the central Andes, the total amount of shortening, so the cumulative amount of shortening, is much more significant than if you go southwards and northwards. And actually, there's a reasonably sort of smooth decrease in total shortening southward and northwards away from this bend in the subduction zone, so the Bolivian Auric line. So shortening here is of the order of, I think, up to about 400 kilometers since the Eocene. And if you go southward and northward, it becomes less and is more of the order of 50 to 100 kilometers or so.
Okay. So yeah, those were my two questions. Anyone else? Okay, so I think we'll stop there. I thank you very much, Wouter. It was really interesting. And thank you everyone for